Alright, so number one, I don't think we can actually be very precise about, but if we do make the turbine taller, we will have a higher average wind speeds, so that will make us generate more power. Right? It's not going to be a huge amount, but maybe 1%, if we make it 100 feet taller, maybe 2%, something. If we increase the blade length by 1.5 times, what's that going to do?
2.25 times.
Right. So we're going to be increasing the radius by 50%, right? So then we have to kind of square that effect. So I'll take your word for it. So 2.25 times more power.
Yeah.
Okay, that's a lot more power. Right? It's a lot more power. Increase the wind speed by 1.5 times.
3.375 times more power.
So that we'd have to cube 1.5. So it's 3 point what?
375.
Okay, so like 3.4 times more power. But we kind of can't really increase the wind speed. We need like nature, weather to do that for us. What's that?
We can use a fan.
We can use a fan.
More power.
Infinite
energy. Just make a wind turbine attached to a fan.
Stuck a wind turbine?
Like no, we're not doing it. Alright, and it will increase the air density by 1.05.
1.05 times.
Of 5% increase in power. 1.05 times means 5%. Alright, fantastic. Waves. So I actually didn't read the entire first objective for wave power. Let's do that real quick. Describe the principle of operation, Jacob, of an oscillating water column, ocean wave energy converter. So this is really narrowing us to just a single style of wave power device. And then in the teacher's note is students should be aware that energy from a water wave can be extracted in a variety of different ways, but only a description of the oscillating water column is required. So I am going to show you some other ways, but the oscillating water column is all that we need. What does a water column mean?
A column of water.
A column of water. Would you envision vertical or horizontal?
Vertical.
I would envision vertical also, I don't know why. Probably because I know what these things look like. And then Liam's going like this, right? So we need a water column that is oscillating, right? So we're going to somehow make power by using wave energy to oscillate a water column up and down. How do you imagine we would do that? It starts with T. Not time.
Tricks.
Not time. Something that every other form of energy production had. Turbine. Right? Right? But not so much a turbine for the water, but a turbine that's using the air above the water. Alright? So that's what our oscillating water column, ocean wave energy converters are going to do. So I have a bunch of links that I haven't preloaded. Hopefully that's not going to backfire on me. But anyway, so before we do that, so generally these things involve the air pressure above the column of water that's spinning a turbine. So I have a couple of different video clips. I might bypass some of them. Yeah, so this is actually a pretty good one. This is probably the best one out of the bunch. So this is actually a slanted column of water that is, as the waves come in and out, that column of water is going up and down. And then as the air goes up, it spins the turbine one way. As the air goes down, it spins the turbine the other way. What's that?
It's not really vertical or horizontal.
Yeah, it's like slanted. Right. That particular one is slanted. Right. So that was a pretty good one. Now I forgot for my next video clip, which I do want to look at. I do think that the audio is important. So let me get that plugged in. Am I right? We have till 39. Does that sound right?
Yeah, because there's 36 last time.
You can see it on the board.
I had it on the board, then I stupidly erased it.
It's on the board. It's still there.
Well, that's my memory that contributed to that.
Once up to 41,
Right, so this is video footage of what I think is like an experimental oscillating water column ocean wave energy converter. And all that you're going to really see is like where the air comes out after it's passed through the turbine. So you can see that it's windy, but more importantly, you can hear that it's windy. So I'm sorry for the low quality. This is the only like real footage I could find. So there's where the air comes out. You kind of hear the waves. You can hear waves. sounds like when wind hits a microphone. And it's intermittent, right? It's not constant, it's intermittent. It's only when the water's like coming up and then going back down. Yeah, you can see it a little bit with the flattened shirt, right? That's about it. I think that's enough. What was your question?
Does it generate energy both ways?
Sure. And it would be alternating current actually, since it switches direction, but the frequency is super low. Alright, I mean if we're putting this into the electric grid, we need 60 hertz, alternating current. That was like what, maybe once every 3 seconds? So that's like 0.3 hertz. Not fantastic. I do have another file you can take a look at. In the interest of time, I'm not gonna show that. Now there are other styles, and I'm not going to click on any of these links. I have animated things here that we can look at. So both of, well this one, let's look at this one first. This is essentially a buoy, right, that we have attached to the bottom. And as the wave goes past, it just kind of shakes this thing a little bit, right? It just rotates it a little bit. But that's fine, because we have like a counterweight in here that will have like an out of phase oscillation with the rest of the thing. And if we have like wires in one of these and a magnetic field in the other one, we will have movement of the wires, or relative movement of the wires in the magnetic field, and we can generate electricity by that. So this is called a Salter duct. I guess because these things, float like ducks. I don't know where the Salter part of the term comes from. Yeah, maybe it gets salted, maybe the salt crystallizes on it, I don't know. So that's just a different style. It's not the style we really need to know about. This is a different kind called a hinged contour device. That again, like we just stick something in the water and the waves push on it and pull on it. And then this one, I guess, has kind of like a piston attached to it. So we would use that rotational motion, we would turn it into linear motion here, and then we can have our generator. I guess the generator is actually up inside here. So those are some other ways that we could tap energy from waves, but the oscillating water column is the only one that IB says we should know about. All right, so do we do this? Not really. Not really. The first commercial wave farm started in 2008 in Portugal and sold power for about 2 months. Yeah. Matt, we all right? Sold power for about 2 months. So, the first to do anything costs a lot extra money, right? And most companies are going to not put the money into that research to do that. So the company that did this, and it was like 2 megawatts, right? That's something. But, in 2008, I think that's when the economy kind of went sour, started to go sour, and the company just stopped. Like they couldn't do it. Like they weren't making money. So it stopped operating. The next one I could find that went online was 2010, right? In the United Kingdom, Scotland had like a 3 megawatt wind farm that was finished, and I think it's generating power right now. The first phase was finished. The total project would be 3 megawatts. I don't think any other phases have started. So I think they are selling some electricity, but a relatively small amount. And then there are projects that are well underway, again, pretty small scale. Australia and Oregon, and those are the only 4 incidents I could find as of like last week. Yeah, Liam.
So did they spend all that money in 2008 and get it built?
Well, when companies go bankrupt, their assets get sold, and then the people that started the company, they can start a new company. But if you go bankrupt, that's kind of it. There's different terms of bankruptcy, and I don't know how it works in Portugal. But the creditors would have, if they wanted it, taken ownership of it. But yeah, I don't think it was probably dismantled.
So why?
Why what?
It's such a waste of money. Why wouldn't they just?
But you can't make money unless you spend money. It's like spending money doesn't work
Why
out.
wouldn't the country just make sense to just build this?
There's no competitors. They're the first ones.
No, the people who took over, the people who.
Oh, the creditors. Oh, because the creditors, the creditors aren't in the business of making money. They're in the business of making money. They're not in the business of selling electrical power and engineering stuff. They're in the business of giving somebody money to get a return on their investment, right? Patrick.
Why do we bother learning about these if they're only 4
Ha.
sentences?
Well, not only that, but I mean, this curriculum was written 10 years ago,
So everything.
right? So that predates this one even.
So then
The
why-
first time I taught the course, I knew about this one. But when they wrote the course, this what? Yeah. So I guess they thought it was going to be more significant. And it should be. Like, why the heck aren't we doing this? Like, we should be, but we're not. All right. Anyway, we do want to make this quantitative and push to see if we can finish this. So the form of energy that's being delivered to our device would be gravitational potential energy in the water. It's actually not kinetic energy. We're not using the water to spin a turbine. It's the water that's elevated above like the regular ocean level that is pushing on this column of air like up and down. So the starting form is gravitational potential energy in the water. Yeah, we can trace that back to kinetic, right? The energy is in the water because wind was pushing on it, whatever. But it's this gravitational potential energy in the waves that we're talking about. And the amount of wave power that we can deliver is definitely going to be based on the height of the waves. It's going to be based on the frequency of the waves as well. If we get one wave every 10 seconds, we can't get nearly as much power as if we got one wave like every 1 second. The density of the water would be significant, like the more mass we can get above the regular ocean level, the better off we'd be. Now, there's an equation, yeah, there is an equation in your data book, it's the second equation, and I think does it spell out power per unit length? Is that how it does it? Alright, so that is our wave power expression, right, that we want to make some sense of though. So one of the things we'll notice in there is, and maybe, I don't have all these memorized, so what the heck is it?
1/2
A squared
area squared.
rho GV.
Alright, so the A in our wave power expression is not area. Alright, that's the amplitude of the wave. So the most important factor in the power per unit length. So when we talk about like ocean waves, if here's like our beach, right? We have waves that run parallel to the beach. So this is not the total power that a wave can deliver, it's the power like per meter that we can get out of a wave. So we have amplitude squared, that's the most important factor, is how high above regular ocean level the water can get. The other terms, so that could be a point of confusion, that in the other equation for wind, the A is area, and in this equation for waves, the A is amplitude. So we definitely want to keep that straight. The other term should be familiar, right? The rho is the density of seawater. It's slightly more dense than like freshwater, but not appreciably so. Acceleration due to gravity, since it's potential energy that we're dealing with. And then V is the wave speed. Now, I'm putting this in red because I guess it's important. The amplitude of the wave is not the total height, like from the trough up to the crest, right? It's like half of that total height. So we have to keep that in mind. Alright, I do want to attempt to help us derive this expression, and then we actually have 10 minutes, so I think I can slow down a smidge. What are these supposed to be? Those are supposed to be waves, right? I don't really have rectangular waves, but it makes the math a little bit simpler, and it's actually not that bad of an approximation. It would be, yeah. Surfing would be easier or harder?
Harder.
It'd be easier.
No, it'd be harder.
No, because if you stand at the back of your board, the whole wall of water would be pushing on you.
Yes,
Yeah, but you
need to
fall
aim
over
the
because it's
board
vertical.
Whatever.
against the
Can't
wave.
stand flat on a board.
So here's our total wave, right? But it's only the water kind of above the regular water level that is going to contribute to the power. So we actually only care about a single amplitude, right? So like equilibrium position to crest, right? So we only care about that red amount of the water, all right? So what are we trying to do? We said the power is going to be the rate at which we can extract gravitational potential energy from the water. We know that gravitational potential energy, or at least the change of potential energy, is mass times gravity times change in height. So some of this already, we can see how it played out in our eventual equation. We already have our G. I guess that's actually the only thing. So let me separate out the G. Because that we already have, we don't have to do any more deriving for that. Alright. What should we tackle next? Let's, mass, fine. Yeah, that's pretty easy. So mass, as in our last few types of power production, is density times volume. So yeah, let's throw that. Yeah, those are great suggestions, Patrick. Alright, so now we have two parts of our eventual expression. And all we need to do now is figure out a way to turn volume times height divided by time into 1/2 amplitude squared times wave speed. So let's do the volume, no, let's do the change in height part first. The change in height is actually going to be the same thing, ooh, now I'm fumbling. I was going to say it's the same thing as the amplitude, but do I mean that? Shouldn't P be above
Shouldn't the change in height be 1/2 it?
Yeah, that's what
Shouldn't the change in height be 1/2 the amplitude?
Because it's half of.
Let's proceed with that, and I don't think we're going to get to 1/2 using.
No, it's going to be half the height. Half the change in height.
Wait, the change in height is in equilibrium to than it is just the amplitude.
Then it's just the amplitude.
All right, so let's not do that yet. Let's not do that yet.
The real question is what change in height is.
Yeah,
Yeah,
yeah. So let's not do that yet. Let's not do that yet. Let's play with volume. Let's play with volume. So the volume that we care about is the volume of, well, not just that rectangle, but that like three-dimensional rectangle. So we want the volume of that. The volume of that would be what that would be like this dimension times that dimension times that dimension, I think. Right?
Yeah.
Alright. So this dimension is, so I'm just going to try and figure out what the volume would be. That's half the wavelength. And the wavelength is even labeled here. So that should be half the wavelength, lambda over 2. This dimension is the amplitude, right? No? This dimension here is the amplitude of the wave. And then that dimension there would be like the length of the wave. Yes? Okay. So volume is lambda over 2 times amplitude times v. I'm going to put that in for v.
I feel like that made it worse.
No, it doesn't make it worse. It makes it better. I haven't done anything with my delta H or my T yet. But I want to take the length and move it to the other side because our eventual equation is for power per unit length, right? Rewrite that up here. So power over length is, I got my gravity, that's good. I got my density, that's good. I have one amplitude, that's good. And now I have lambda over 2, so that stuff's pretty set. Lambda over 2 times height divided by time. I think that's what I have left. I suppose we could just pull out the half also, right? Let's do that. That gets us closer. Alright, so that stuff's all set, and then I have lambda and height and time. Alright, so let's try and deal with the lambda. We don't have any lambdas in our, oh, I erased it. We don't have any lambdas in our equation. So what we're going to need to do is turn the lambda into a wave speed. Okay? I'm going to erase this. Speed is frequency multiplied by wavelength. Right now I have a wavelength, which is speed divided by frequency. I don't know the frequency, but I know the frequency is the number of waves per second. Number of waves per second. I think I can just do that. Is that okay? I think that's okay.
Wouldn't it be VT if F is 1 over T?
Did I do that wrong?
I'm
No.
not
I
sure.
don't think so. I think I'm good. All right, so let's proceed with that and see where that gets us.
Yeah, this is
Yeah.
because F is, if it's like per unit time, then F
Number
would
of
be-
number of waves per unit time.
Yeah.
All right, so let me think about that. divided by the frequency is number of waves per second. Number of waves per second.
And V is velocity, right?
Yeah, V is totally velocity. I'm just looking at my little
And if
cheat sheet here to see how that's going to help.
well, if length is measured in meters and
Right.
V is meters per second
Right?
and T is seconds, then
Right.
it makes sense if it was VT.
Yeah.
Because then it's meters instead of meters per second squared.
Yeah, fine. I'm not having any great ideas about talking about that anyway. So this is certainly, we know that wavelength is speed divided by frequency. Dimension of, yeah, analyzing the variables, it would have to be true that speed multiplied by time would give, I mean, meters per second times seconds is exactly right, gives us meters. So yeah, so sorry, I'm falling a little bit with that, but that's going to be true, and it's going to help us get rid of that t as well. So let's put the vt in for the lambda and see what else we need to do still. So now I have v times t, and then I still have my delta h over t. So the t's can cancel out, and if the change in height is the same thing as the amplitude, which I'm comfortable that it is, because this is the only usable part of the wave that we have, then the delta h does turn into an additional amplitude. And then I think we do get what the data booklet expression is. So anyway, you saw me fumble in a couple of places. I don't think this is an easy derivation at all. The good news is I think I've only seen one question ever where candidates were asked to derive it. And I would hope that even if it's tough, and even if you stumble a little bit like I did, if it's a 4 or 5 mark thing, you can get 2 or 3 marks. All right, so we didn't really get to look at an example, so maybe we'll spend an extra 5 minutes. But that's it. I mean, that is all of the instruction for the ways that we produce electricity. So I did give you the renewables handout already, so there are like 6 different problems there. Plan for it to take you 2 to 3 minutes per problem. So you might just want to take 15 minutes of lunch today, so you don't have to take that home with you, but that's your call. So have an enjoyable break, right? Remember to do a fun 10 to 30 second video. I've started doing some also, and I've had some fun doing it. What I'm not having fun at is figuring out because I want to do a lot. I've only done 4 so far, and I'm starting to draw blanks for being entertaining. So
Just gotta find
I'll think
different
about
spots.
it when you anticipate, just have me come over one day.
You just gotta find different spots to do.
no, because I want it to be entertaining beyond
Well, are you
like
going to
the
stop
spots.
here? Are you really, like,